All right, hey y'all, I'm gonna go over this whole lecture instead of just the last page, which I think is the most important, but just in case we miss anything, I think it'll be good practice to do some extra Lewis structures. So the first Lewis structure it asks us for is carbon monoxide. So if you remember, we have a few rules when we're doing Lewis structures. This first one is we're going to count valence. So we first count the valence electrons. If anybody missed this, now's the time for me to maybe go over it. The valence electrons are determined by the column the thing is in. So the first column, it's 1, second column's 2, third column's 3, fourth is 4, fifth is 5, 6 is 6, 7 is 7, 8 is 8, and so on. So if it's in the 8th column on the periodic table, it's got 8 valence electrons. If it's in the 3rd column on the periodic table, it has 3 valence electrons. Okay, so that's step number 1. Step number 2 is we put the first atom written, that's going to be the least electronegative, in the center. If there's only 2 atoms, there is no central atom, but in cases where there are several different atoms, the first atom that's written in the formula is going to be the one in the center. Third, we're going to bond and give everything an octet. But B, BE, and H. Remember, an octet means something has 8 different electrons around it, 8 electrons around it, and the bonds count for 2. Fourth, we're going to recount valence. We're going to recount the valence electrons, and we're going to go ahead and adjust as necessary. Or adjust if needed. Okie dokie. So let's go ahead and do some of these. We've got the very first one is carbon monoxide. So following these steps, we first count the valence electrons. Carbon monoxide is a carbon and 1 oxygen. Carbon is in the 4th column. It has 4. Oxygen's in the 6th column, it has 6, and therefore we have a total of 10. Yeah, buddy, you win. My dog wins. He's going to get a treat, and I'll be right back. Hold that thought. Here, Bubba. There you go. Okay, I have some happy dogs now. All right, so now we know the total number of valence electrons. The next thing we do is we're going to put the first atom in the center. If there had been more atoms, we would have put carbon in the center. There's just only 2, so there is no central atom. Then we bond them together with a bond, and we give everything an octet. Remember, the line already counts for 2, so looking at this carbon, it has 2, so it needs 6 more. 3, 4, 5, 6, 7, 8, always in pairs. We look at the oxygen, same thing. 1, 2, 3, 4, 5, 6, and again the line counts for 8. Now they both have 8. Step number 3 was step number 4 was we count valence and adjust again. We have 2, 4, 6, 8, 10, 12, 14 total electrons now. Remember, we can only have 10. So something has to give. Anytime you have too many, you cross out 2 lone pairs on either side of two lone pairs of an atom on each side, and you draw a line between those 2 atoms. You can't just choose a random atom in the structure, which we'll come back to. You always have to cancel it between, or draw the line between the 2 that you withdrew the electrons from. Now, if we count, we have 2, 4, 6, 8, 10, 12. So now we're at 12. 12 is still not 10 that we're going for. So what do? We cross out those, and add a 3rd bond. And that's what our final structure should look like. So carbon monoxide is C. It's got a triple bond, O, ... 2, 4, 6, 8, 10 electrons. All right, now we can do CH2O. So for CH2O, follow the same exact situation. Step number 1, we're going to count the valence electrons. Carbon has 4, plus there are 2 hydrogens, and each hydrogen has 1, plus 6 for a total of 12. Okay, so we need 12 valence electrons at the end. We draw the carbon in the center with the hydrogens over here and the oxygen over here. We bond everything together. Now we have to give everything an octet. Everything but H. Hydrogen will never have an octet. Remember, never, ever, ever, even when pigs fly, will it have an octet. Carbon here needs 2, so now it's got 2, 4, 6, 8. And then oxygen, we need to add 6 to it for it to have an octet. Now oxygen has an octet as well. When we go to count up electrons, 2, 4, 6, 8, 10, 12, 14. Oh no, we got 14. That's too many. So what do? We remove a lone pair between two atoms, and we double bond those atoms. And that's our final structure, 2, 4, 6, 8, 10, 12. So when I go to write it, carbon, we get that. Alrighty, so next is boron trifluoride. Boron trifluoride is BF3. Boron is one of these exceptions. It doesn't need an octet. Boron will pretty much always have 3 bonds. Beryllium, by the way, will always have 2 bonds. So in case you come across that in your homework, it's good to know. So first I put the boron in the center with 3 fluorines around it. I'm going to go ahead and add electrons. So they have 8. So this fluorine currently has 2 and needs 6 more in order to have 8. Same thing with each of these fluorines. For the boron, we don't give it an octet, again, because it's an exception, it doesn't need it. We first count electrons to make sure, oops, and that's what I forgot to do, 3 from the boron plus 3 times 7, because there are 3 fluorines and each one has 7, because it's in the 7th column, gives you 24. So we should expect 24 electrons when we're done. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 24 electrons and we are good. That is a structure of BF3. And last but not least, phosphorus trihydride. Phosphorus trihydride is PH3. Phosphorus has 5, and each hydrogen, again, has 1. Phosphorus is in the 5th column, hydrogen's in the 1st, and this gives us a total of 8. Put phosphorus in the center, 3 hydrogens on either side. Give everything that we can an octet, and we know hydrogen can never have an octet, but phosphorus has 2, 4, 6, so it needs 2 dots, 7, 8. Now it has a total of 8 around it. And when we go to count the total of electrons, we have 2, 4, 6, 8. Ah, look, we don't have to do anything, no double bonds or anything. So that is the structure for PH3, or phosphorus trihydride. Okay, so for polarity, we talked about cis and trans, C2, H2, F2. This is going to be the cis. We'll do the trans over here. Remember, we talked about cis meaning same. So if we have a fluorine over here on this side of this, let's draw a carbon here. I was going into full OChem mode here. And in OChem, by the way, you don't draw carbons. Weird, right? So if we draw this structure out, and I guess you would be able to do this Lewis dot structure, but the most important part is I want you to pay attention to the fact that these fluorines are on the same side of this carbon, and these fluorines are on opposite sides. The point of this lecture isn't the naming. I don't care if you really got cis and trans. I won't ask you to draw a cis and trans compound. You will need to in the next semester probably. But what I want you to pay attention to is polarity. So remember, we talked about if you have something paired with fluorine or something electronegative. By the way, I guess I could go back in time a little bit. I'm kind of trying to skip a lot of stuff and go quickly. But electronegativity is up and to the right. Electronegativity. Electronegativity is essentially the an atom's desire to have electrons around it. So if something is really electronegative, it really likes electrons. So when we first talked about drawing these Lewis structures, we said that these two electrons in here are shared. They're equally shared. That's a covalent bond, but they are not equally shared. If you have an atom that is more electronegative than another atom, what we have is what we call a polar bond, meaning fluorine really likes electrons, so it's going to pull these two electrons closer towards it. It's kind of a jerk. And what that does is it leaves carbon over here with a slightly positive charge because the fluorine took the electrons away. And so we draw this thing, which is called a dipole arrow. Dipole arrow. And again, kind of the important point is that fluorine is up here. It's really electronegative, so it's going to pull electrons away from that carbon. All right, with that in mind, we're going to look at these molecules. So between this carbon and this fluorine, fluorine is pulling electrons that way. And between this carbon and this fluorine, fluorine's pulling electrons that way. Well, if this is, I don't know, a little kid getting pulled by their arms on either side, the question is, would this kid move if they're getting pulled up and over this way? And the answer is yes, they'd move. They wouldn't move to the left or to the right, but they would move up. So these two forces, if you pull somebody this way and somebody this way, they'll actually move up. And because they'll actually move up, this thing is what we call polar, meaning there's an unequal distribution of electrons in this molecule. There's fluorines up here are getting a lot more of the electrons than the other stuff down here. Now let's look at this one. Here we have somebody pulling this way and somebody pulling the opposite, equal and opposite direction. If you have somebody pulling this way and somebody also pulling the equal and opposite direction and they pull as hard as they can, it's like an equal game of tug of war. They're not going to move. So even though this looks like it might be uneven, when you really think about it, the pull this way cancels the pull that way, and there is no unequal distribution of electrons. So this would be nonpolar. All right, I'm going to skip some of this stuff just because we discussed it in a lot of detail, and I wasn't planning on getting into molecular and geometry and stuff like that either. We're just going to move straight onto this. At least I wasn't going to get into a lecture on electron and molecular geometry. I have provided that for you in an alternate video. But what I will do is remind you how we filled this out. So, do you guys remember we start with 1, 2, 2 3s, and 3 4s. And we said this was 0, this is 0, 1, and this is 0, 1, 2. We said if it's got a 2, its electron geometry is linear. If it's got a 3, its electron geometry is trigonal planar. It looks like a little triangle in a plane. And same with over here, trigonal planar. And if it's got a 4, it's got 4 electron groups. Its electron geometry is tetrahedral. Tetrahedral and tetrahedral. All right, and then we talked about its molecular geometry. If it has 0 lone pairs, its electron geometry has to be the same as the molecular geometry. The molecular and electron have to be the same because in molecular geometry, remember, we're looking at atoms, and the electron geometry, we're looking at electron groups. So we're looking at the shape of atoms over here, but over here we're looking at the shape of the electron groups. But when there's 0 lone pairs, these two have to be the same thing because the atoms are attached to the electron groups. This one must be trigonal planar. But if we have 3 electron groups and trigonal, let's see, I think we talked about this as an example. So here we have 3 electron groups, 1, 2, 3 electron groups, and one of them is a lone pair. Again, we're only looking at the atoms. So from this oxygen to this nitrogen to this chlorine, it looks like it's a bent thing. That's why this is bent. Over here, if it's got 0 lone pairs, it has to be the same. So it's tetrahedral. If we have one thing missing, like we talked about, NH3 was our example, I believe. So here we have 4 electron groups, 1, 2, 3, 4, and one of them is a lone pair. We said that that it went from being tetrahedral to now kind of looking like a little pyramid. And that's why it's trigonal. Pyramidal. Last but not least, we have water. It was an example that we gave. So we took another one of these off. So we still have 4 electron groups, 1, 2, 3, 4, but now 2 of them are lone pairs. It's still got a tetrahedral. The electron groups still form tetrahedral, but the atoms themselves are back to being bent. Then we have these bond angles. We said this was 180 degrees if it's linear. If it's trigonal planar, there's a plane and it's a triangle which is put into a plane. So essentially if you took a circle and divided it by 3, you'd get 120 degrees. If you take off one of those lone pairs, so this we did BF3, I guess I am going to give a brief lecture on this. I can't help myself. Oh no. So if we took off one of these and replaced it with a lone pair, remember we said that that's going to squish these two things together. So it's going to squish them a little bit. This becomes less than 120 degrees. Now if we have something tetrahedral like CH4, which remember actually in 3 dimensions looks like a twisted X, look like an X. Well, I can't do it, never mind. It looks like an X, but twisted. This was 109.5. We said if we replace one of these with a lone pair like we did here, so we still have 4 electron groups, but now one of them is a lone pair, it was going to be less than 109.5. It squeezed them together. And now if we replace 2 of these with lone pairs, so we took this one and that one and replaced them with lone pairs, it's going to squeeze them even more. So we said it was less than 109.5 because us chemists are smart. All right. Now we're going to use this information to fill out this table. The table you have been waiting for. All right. So step number 1 is going to be count valence electrons to build the Lewis structures. So in all of these, don't forget that your ultimate objective is to be able to build a Lewis structure. If you don't build the right Lewis structure, you can't possibly discern this information over here. So we have to build the right Lewis structure first. So going through here, let's start with the carbon. Let's start with this one. We'll just do one at a time. So we know carbon has 4 plus 3 times the 1 for the hydrogen plus 7 for the bromine. So that's a total of 14. So we're looking for 14 valence electrons when we draw the Lewis structure. So I'm going to put carbon in the center. Remember our rules? 1, 2, 3. And then it says it has a bromine on it. Good. One thing I've seen a lot of people do is mix bromine up with boron or anything like that. You're going to really need to know those names. So make sure you're paying attention to the atom that you're using. All right, now we give everything an octet. Carbon currently has 1, 2, 4, 6, 8, but bromine needs 1. So I add 6 more. Now it's got a total of 8. All right, now we count electrons. 2, 4, 6, 8, 10, 12, 14. Hey, we got 14. We're good. All right, so now all we do is count the electron groups around the carbon. We're looking only at the center atom. We're looking only at this center atom right there. That was supposed to be a star. All right, so it has 1, 2, 3, 4 electron groups. None of them are lone pairs. So we go over here. 4 electron groups. None are lone pairs, which means the electron geometry on this has to be tetrahedral. Its molecular geometry has to be tetrahedral. And now we look at polarity. Well, remember that carbon-hydrogen polarity we say is negligible. But this is carbon-bromine. Bromine is over to the right on the periodic table. It's electronegative. So your question that you should ask yourself is this thing totally symmetrical? The answer is no. Bromine's going to be pulling it that way. If it pulls it that way, then there's nothing else canceling it the other direction. This is absolutely polar. All right. Let's move on to H2S. Actually, I'm going to get some more paper so I can draw these a little bigger for y'all. I would normally edit these pauses out, but I'm kind of busy, so we're just gonna do this. Okay, so H2S. Let's go ahead. Like everything else, we're gonna start by counting the valence electrons. We have 2 times 1 plus 6 for a total of 8. Now something that really bothers people on this, and I understand why, is because it has an H on it, and you want to start with an H and put stuff around, but remember, H's always have to go on the outside. There's only one way you can build this. It's like that. That's it. Or, you know what you probably would have built is like this. So let's build it that way. All right, so once we pair everything, we have to add an octet to everything. We got 2, 4, 6, 7, 8. Okay, so 2, 4, 6, 8. All right, so now we count electrons, 2, 4, 6, 8. That worked really well because we were trying to get 8 up here. So this is our structure. The problem is we drew it like a line, but let's figure out what it is. It has a total of 1, 2, 3, 4 electron groups, and 2 of them are lone pairs. So we go over this thing, and we see that 4 electron groups, 2 lone pairs is tetrahedral bent. So it kind of looks like this, the bent thing. So when we go to draw it in our table, I think it would really help us to draw it bent like this, to see that there's not an equal and opposite pole for the sulfur. So this thing is tetrahedral electron geometry because it is 4, but its molecular geometry is bent. If you drew it like a line, it would look like it's not polar, but because it's got this pole going up here and this pole going here, it is polar. All right, let's look at CS2. Okay, just do it this way. So CS2. We know carbon has 4, and each sulfur has 6 because it's in the 6th column for a total of 16 valence electrons. We're going to put carbon in the center and sulfur on either side. Now when we go to add the octets, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. When we go to count these though, we have a total of 20 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So what do? We got to remove 2 lone pairs. Here's the number 1 mistake. You don't just choose any 2 lone pairs you want. You have to remove them between the 2 atoms you're going to draw a bond between, because that keeps them having an octet. So I'm going to take this carbon and this one, and I'm going to draw a bond. I could just have easily done this or over there, down there. Doesn't matter. But the important thing is you draw that bond between the 2 that you removed on either side. So now if you count, sulfur still has 2, 4, 6, 8. Carbon still has 2, 4, 6, 8. They still have octets. You can't remove the fact that they have an octet. But now if you count, you have 18. So we still need to get to 16. So we're going to remove another 2, and draw. And now we have a total of 2, 4, 6, 8, 10, 12, 14, 16, and we are good. So our CS2 end up looking like this. Okay. It doesn't matter where you put the lone pairs. All right, so how many electron groups do we have? We have 1, 2 electron groups with 0 lone pairs on that carbon. And so this is linear and linear. Yes, there's a slight, very small pole between these, but they're equal in opposite direction. One pulls this way, one pulls that way, and so it is not polar. This next one, I updated this to CO2. So if you're using the one online, it's CO2. If you're not, you did CO. You already know the what CO looks like. It was at the beginning of this lecture, we did CO. And we also said that it's gonna be linear because there's only 2 things. But let's go ahead and do CO2. So CO2, we put a carbon in the center and an oxygen on the other side. It has a total of 4 plus 2 times 6 for a total of 16 electrons. Add our dots. And when we count, we have a total of 20 valence electrons. We know that that's not right. So you have to remove 2 lone pairs from either side of the atoms you're going to draw the bond between. So we moved one there, and drew a bond between them. Now you have 18. That's not good. We want 16, so we do the same thing. Remove, remove, draw a bond. So now our carbon dioxide, I just like to even things out. Each one has 2 lone pairs, but you could have drawn it just like we have it here. Once again, you have 2 electron groups. 0 of them have a lone pair. And so this is linear. The molecular geometry also must be linear. And then once again, you have the equal and opposite pole because they just form this line. So it is not polar. BCl3, one of my faves. All right, so we got BCl3. We know it's got 3 valence electrons plus 3 times 7 from each chlorine for a total of 24 valence electrons. We're going to put boron in the center with a chlorine around it, all 3 chlorines around it, and give everybody an octet. Do I give boron an octet? Heck no, I don't, because I should recognize this one is the exception. Remember, boron and beryllium, and also H, don't have to have octets. If I go to count electrons, I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I got 24 valence electrons, and that structure is correct. All right, so if I write it in here, cool. Now, if I go to count the electron groups, 1, 2, 3 electron groups, I see 0 lone pairs on that boron. So we go to our chart. 3 with 0, it's trigonal planar, trigonal planar. Okay, and then the question of, is it polar? Well, I think the best example I have is I have 3 dogs, and I have this toy. It's got like a ball right here that they play with, and then this is a rope, and this is a rope, and this is a rope, and it's formed like this. And all 3 of them will get over here, and they'll play tug of war, and one will pull it this way, one will pull it that way, and one will pull it that way. And my question is, does the thing move? And the answer is no. They're all pulling in equal and opposite directions, and so this doesn't move. And that's why this molecule right here is not polar. Those electrons, even though they're getting pulled in all sorts of directions, they all cancel each other out, and there's no uneven distribution. It's not like this one's winning. If I were to replace this Cl with like an F, where these 2 are still Cls, and remember this one's stronger, it's further up to the right, then it would be polar. But as is with the Cl, they're all the same, nothing's happening. All right, last but not least, CH4. Okay, we know there's 4 from the carbon plus 4 times 1 from each hydrogen for a total of 8. We put the carbon in the center, we add the 4 hydrogens. And then we calculate. We got 2, 4, 6, 8. Hey, we're good. Yay, us. It already has an octet. There's 8 electrons. CH4 looks like that. This has 1, 2, 3, 4 electron groups. 0 of them are lone pairs. So this must be tetrahedral, 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 and let's look at its polarity. It has 4 things all pulling in equal and opposite directions. Because they all cancel each other out, it is not polar. Compare that to up here, if you remember. So here, all 4 hydrogens around a carbon. Here we have 3 hydrogens around a carbon and something else, and we said this was polar because it was not all even. All right, y'all. Hopefully that helps you. And if not, well, study hard. And I will see y'all soon. Bye.